So tonight I'm going to talk about DeepSeek, in particular about their floating point 8 usage, why they did it, what it is, and how they did it. We'll find out that theirs is kind of unique, and we'll talk a little bit about the situations here. If you're new here, if there's something that I say that you disagree with or you don't understand, just say so and we'll stop and discuss it. We all learn from each other. And I think that's one of the great things about this group, okay? Okay, great. Actually, I'm gonna stand up too, just so my back is killing me. It's been raining here, and I'm getting old, and every time it rains, things hurt. Okay. Okay, so what does FP8 mean? FP, if you're not familiar with it, is floating point, versus an integer number or something like that. So we have a cute little example there, 1, 2, 3, 4 to the, if you have something like 1, 2, 3, 4, and it's to 10 to the negative third, you have two parts. The 1, 2, 3, 4, the integer part, is called the significand, and the minus 3 power of 10 is called the mantissa. So if you see me reference each of those terms, I don't know if I do, that's what they are. Typically, we use 8 bits to represent that, and that's one of the reasons we want to do this, because fewer bits means fewer stuff to push around and we can move faster. There are FP8 formats, and let's see, the FP8 form range in use. There's two. There's one they call E4M3, which has 3 in the mantissa. The M is mantissa. And that can represent values from, let's see here. Yeah, I'm sorry. Yeah, significand is shorter. Sorry. It can represent values from negative 448 to positive 448. You get one sign, plus, minus, or nothing is plus, an exponent, and 3 in the mantissa. So you have more precision. You can more precisely define your values. So that's what we use in training a neural network in the forward pass, or that DeepSeek uses, or in general with FP8 we use in the forward pass.
Hey, Jerry.
Yeah.
Is significand and exponent the same?
Yes. I'm sorry.
Okay. Okay.
Depends where you went. Depends where you did your math, I guess.
Okay. And in all the floating point formats, isn't it they assume the first bit is 1? Is that right?
I don't think that's
Maybe I got that wrong, right?
correct, Roger, but
Okay.
yeah.
Fair enough, because I guess you'd need 0. So
Yeah,
okay.
zero's a perfectly valid value, right?
Okay.
Yes. Yeah. Okay. No problem. And then we have another one, the E5M2, that it goes from these larger numbers to larger values. So that's where we need more range. And that's typically in a neural network in the backward pass, when we're propagating values back from the far end of the network back to the beginning of the network and adjusting all the weights and biases as we go through. Okay, there is a section in the NVIDIA docs on this, and it's using FP8 in the transformer engine, blah, blah, blah. And everything we're going to talk about has to do with transformers, because almost all our machine learning today is somehow really close to what the transformer model has. So, don't be surprised. That shouldn't come as a surprise to anybody. Any questions on any of this?
So this information is from the link that you shared down below?
Yes. Thank you, Deb. Yeah, and we are very informal here, so if anybody has a question, please stop. Just say, stop, I don't get this, and we'll discuss it. I may not know the answer, Roger may know it, or Dave may know it, or Ted may know it, or somebody else, may know it, but somebody will we'll have a discussion, I may.
Hey, Jerry, quick question.
Yes, sir. Let me go back to
where you have the E4M3, where 3 is the mantissa, which is, I'm guessing the number can be 10 raised to something up to 3 bits.
Yes.
Which means it's up to 10, the 3 bits could show up to 8 numbers, like value up to 8. Am I understanding that correct? So 8,
That-
10 raised to 8 is, is that right? It could be up to 10 raised to 8.
Not quite following here exactly what that would be.
Okay, I'll just give it one other quick try. Don't want to hold up everybody, but Mentissa is 3. If it's M3, that means 3 bits can be used for the 10 raised to power.
Oh, I see what you're saying. Yes. Yeah, we have the significand and then the our exponent, whatever you want to call it, in the mantissa. Yeah, so that's just the power, right? I think is what
That's
you're
just the
going
power.
for. Yeah, okay.
Yeah. Okay, perfect. Thank you.
Yeah, okay. Yeah.
Yeah, but just to jump in briefly, so the mantissa is actually the decimal part and the
Oh.
exponent's the power.
Oh, yeah,
Yeah.
I'm sorry, Ted.
But the math is right. So if it were 3, it would be like up to 7 if it's 111. Since it's 4 bits, it means
Up
you
to
can have
7.
up to 10 to the 15th.
Right. Okay, makes sense.
I
Okay.
think I caught it already, but I don't have much of a math background, so this is the first time I'm hearing either of these terms, significand or mantissa. What's I kind
You
of
know,
like gathered.
Yeah, for right now, just remember that one, they are different sizes, and we'll talk a little bit about this. But this is the last slide. I think I even mentioned these on. I just wanted to put it out there for kind of the computer hardware guys, actually.
All right, I will replace those words in my head with math thing.
Math thing.
But I think
Put
it's
your
important
Einstein
to
icon.
understand we are talking about 8-bit objects.
Yes.
And so if you need a sign for positive or negative number, that means that the 7 bits you have left, you have to split between, if you're familiar with scientific notation, you have to split between how many decimal places are you going to have and how many are you going to allocate to the power.
Yes.
And so you can allocate a lot to the power and you have a really wide range, but you have very little bit of resolution within each thing. So for like 16 and 32-bit, for 32-bit, I think there's really only one format. For 16, I think there's 2. And so you can imagine that like as you start having less bits to play with, there's some debate. Should you allocate 4-3 or 5-2? How do you best use up your space?
Okay, and so with significand and mantissa, it is do you want more available information to use for the exponent, or do you want more for the resolution, i.e. like number of decimals kind of thing? You only have so much to work with, and then you need to pick.
It's more like the power, I guess, that you want. How far do you want to extend the range to, if you will? Okay, versus and how much precision do you need on it?
So for example, sorry, go ahead, Jerry.
No, you go ahead. You're the mathematician in the group.
No, I don't know. But I was just trying to think that, like a example would be like if you take the E4 M3, you can, let's say you take the maximum value of 448. So that would be like represented as 0.448 times 10 to the 3. And so, right? And so,
yeah, because it would be it's a fraction. It's the fractional part raised.
Yeah, and then in the M3 also there must be a sign bit. And so you've got 2 bits left.
Yeah.
And in those 2 bits, the maximum value would be 3. So that's how I'm kind of deducing. I'm not sure if that's right, but yeah. And in the second case, it would be 0.57334. You have more resolution because you have 5 bits. And then the mantissa is, 10 to the, so you can only do 2. How would that work?
Not sure that
I don't know if that's right.
Your explanation was correct on that, but
Yeah, no, that doesn't sound right.
yeah. We're not gonna.
Oh, it's
We're not gonna.
5. Sorry, I switched it up. 5 is for the exponent.
Yes. Yes.
So it's 10. You have 5 bits for the 10 to the power of
2 to the
whatever.
power.
So it'll 2 to the
Yeah.
power.
Yeah.
And so you would have So I think that works out that you have a larger number there
Okay.
because you have 5 bits for the exponent.
Okay.
Hmm.
Cool. Cool.
Something like that. Yeah.
Yeah. We can work the math. I'm just going to trust the values they gave us were correct.
Hey, Jerry, I
Yes,
know
sir.
we're still like on slide 1,
Yeah.
but just so that people don't get thoroughly confused, I do believe that when we're talking about floating point FP32, FP8, that the exponent is powers of 2, not powers of 10.
Oh,
Okay.
yeah.
So if people are a little confused, like where does this 448 come from? It's because it's a number between 1 and 2 times 2 to the whatever 15th power gets you, I think, I haven't checked it, but like gets you to 448.
Yeah, it definitely, this is, it's definitely a limited structure, and we just have to play games with it on how many bits we're going to give for this and how many bits we're going to give for that. Plus, we have to have a sign bit. That's if we want to have negative values, which we do. Okay.
Yeah.
All right, I'm going to move on. So why use FP8 the model? Well, the bottom line is it's faster. If you only have 8 bits to move around, that's faster than moving 16, which is faster than moving 32, which is faster than 64, blah, 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 blah. So it's faster. And just as a preview where we're going to end up, they're talking FP4 in the next gen NVIDIA processors. So, we're getting smaller and smaller and smaller, and that makes the problem we're going to talk about in a few minutes even worse, but I guess they'll solve it. So in theory, that should make us twice as fast because we have less to move than doing this in 16-bit. Okay, that's theoretical. In actual, it's about 1.48 because there's no such thing as a free lunch, and there is some overhead in doing that. But still, you're going from 400 teraflops on some of these accelerators to 570, and that's a lot more data to push around.
Hey, Jerry, does that include memory access issues, or is that just the flops?
I believe it's pure flops, Roger. I think this is like, on the hardware, I don't care where it goes type thing, but, I could be wrong on that. I'm just going to say that it's probably, it's equal measurement, so the relative performance is probably valid regardless of how you measure it.
Okay.
Does that make sense?
Yeah, so it's in practice, not just the specs then.
Yeah. The specs say
The whole
2, if you're a mathematician, you do that and you get twice as much. No, you get like 1.5 times as much because there's no free lunch in computing. They use memory, take less energy to store, and move values. Good, great, all great. So FP8 is natively supported by some hardware and software. Specifically, if you have a 4000XX or later processor in your, consumer level type thing, and I believe it may be only the 4090, come to think about it, that has that. Or you have an H100, the Hopper series that came out, 2022, 21, something like that. And then going into Blackwell, which is the new series of NVIDIA boards that are coming out, they'll have FP8 and FP4. So we're going to talk about FP8, but just think about it, the case being kind of a little bit worse in 4 bits of precision. Now you're really, really, looking at trying to move data faster and things like that. Okay. And NVIDIA has API support for this. They have just-in-time scaling, and they have auto casting, which is when you convert to 16, you cast a 16 because you're going to go call some sort of method or whatever that needs 16-bit numbers, and then you go back, you get the result, and you want to put it back into something else that takes 8 they have auto casting operators that do that for you. So you as a developer don't have to write that, which is really good because you'd probably write A, code that would probably be buggy, B, code that would probably be a lot slower than what they're going to do, and C, you'd have to maintain it and ship that with, your sources with everybody that was using this stuff. So it's not a business you want to go into unless you're, a real chip type guy. All right. The end result is we get smaller models and we get higher throughput because we reduce the memory bandwidth. And memory bandwidth, think of it as a highway. How many lanes on the highway? If you take up fewer lanes, then you can put more cars on at the same time, right? So just think of it that way. And there's minimal code disruption to use it. It's baked into the NVIDIA libraries and things like that you have if you're programming one of these accelerators. And it's bubbled up into most of your, languages the rest of us would program in, like PyTorch, JAX, Python, whatever. There are data types that support this, so you don't have to deal with it as in an assembly level type programming. Okay. And they use the heck out of it in DeepSeek. It's not important that you understand all these operations, but I'll kind of run it through some of these. fprop is the forward propagation, the forward pass they make through it. And you can see here, they come in with a BF16. BFloat is brain float. Brain comes from Google Brain. They're the guys that came up with this format, and now it's been standardized. And it goes into FP8, and then they accumulate here. They do their mathematics at 32-bit, and then output to 16. And you can see, though, inside the actual chip, when they're talking back and forth, everything is whatever you set. So in this case, it's FP8 to the weights and all that in your model and things like that. The degrad, which is the activation backpass, that's also takes from the output gradient, gets converted from 16 down to FP8, and they push it through. And all this, and over here in the weight gradient too, all this is because of performance. This is just to make things run faster. And it theoretically doubles, this thing here I put in bold, it theoretically doubles the computation speed rather than using BF16. But you have a loss of precision. And so the question to ask is, does this loss of precision or loss of accuracy cause issues? And the answer is, yeah, it does, a lot. So that's what we'll be discussing next. Any questions on this slide?
Gary, this may be appropriate later, but I'm just wondering why the master weight is in FP32.
Which one? Master weight.
Yeah, the master weight, and actually the weight gradient's FP32.
Yeah, I'm not sure why they explode that. They'd have it exploded out and explode it back. I'm not sure. I don't know the answer to that one, Roger. I'm sorry.
Okay.
Anybody else? No, have a thought? Okay.
Well,
So
are you
when
asking?
No,
Go
he's
ahead.
asking for these two, the master weight and the gradient out here on the right side.
Yeah,
Yes.
so one of the reasons I was thinking it is that way is because when you do your gradient updates, they can be very, very small and might not fit into like BF16 or FE8. So you don't want to lose the forward pass and the gradient you've computed. So you keep the master weight in FP32 and you still keep on updating the weight. And at some point there'll be a significant change in the weight, and it will, when you convert it into FP8, it will be reflected, but you don't lose your gradient updates, basically.
So it's more of a preservation of resolution type thing?
Yeah.
Yeah.
Is this, Neha, is this to prevent vanishing gradients?
Yes. So say suppose if your gradient was like really, really small, then you are doing forward pass and a backward pass, but your weights are not getting updated because when you go to BF16 from FP32 to BF16, for example, you lose your range. So you basically, whatever gradient you have, you make it 0, so there's no update on weights. So you might go through like loops and loops of training, but not update with weights at all. So that's why you keep the weight in 32, so you're still updating them.
Yeah. Keep that thought. We're going to come back to that because that is a problem. It's very insightful for you to see this early on. Just look at this diagram, in fact.
Yeah, and just a quick comment. If today in PyTorch you use automatic mix precision, that weight will be 16-bit, BF16, and the gradients will be FB32. The reason why I assume they don't use BF16s for the weight is because you're going to be casting it to FP8 anyway. So if you're going to cast it from something, you might as well use the full precision FP32, right? When they use BF, they don't cast it. They actually do operations with the BF16 directly. But if you're going to cast it to something else, then I think, you know, the little extra bit of storage for the master weight is not critical.
Makes sense.
So the master weight, I might have misread what the master weight is then. The weight is what's actually stored. The FP8 is what's actually stored in the GPU RAM, right?
I'm not sure about the terminology, but basically, like, when you think of what is the parameter, that parameter is stored in full resolution FP32. Now, when you need to use that parameter and say you're doing a forward pass and you're going to multiply it by the inputs, then we use the FP8 version of it inside the GPU in order to speed up the computation, the loading and the computation.
Okay. Good definition, Ted.
So one other question.
Oh, okay. Let me go Oh, go ahead.
So in the WGrad, is the weight the FP32 weight?
I think that's saying,
just following the arrow.
Yeah, I think that means they calculate. It's doing a summation of whatever the weights are and everything, and I think they're saying that produces a FP32. I had
because in the other two cases they use the FP8 version of the weight when they do the multiplication on the left side here. Right?
Yeah, I see what you're saying.
I think all three boxes is FP8 math, and the accumulation per Jerry. I don't know if you're going to get to the whole tile business. The accumulation per tile is done in FP32.
Yeah.
But the inputs are all FP8.
Okay.
Well, Ted, just a preview. We will get to the tile, but I have questions about it in my mind. So if you speak up, I'd appreciate it when we get there. Okay, I'm going to move us on. Okay, so do people know Tim Detmer? He used to be at UW. He's been like really on the edge of like doing things really cheaply during the pandemic. He had a whole series of these things. He's now, I think, he finished his PhD recently, and he's going to CMU, I believe. He may have started this winter, I don't know, but he's going to be a prof over there. So he's a bright guy. And so anyway, he has this video, this 8-bit methods for efficiencies in deep learning. If you really want to, get down in the weeds with it and how all this stuff works. And I just borrowed a few of his slides, if you will, so that just to give us context as to what the problem is working with 8 bits, okay? So if you look over here at this 3.5, keep your eye on the figure in bold on the left. So what happens when you try to shove that number, shove this whole range of numbers and put them together so that you can continue the signal? Well, if you're using FP8, your maximum value you can have is 127 essentially, because you have the plus and the minus. So these are all positive. So what has to happen is you have to scale everything accordingly. And what happens then? You see this 0.1? It goes to a hard 0. And once it goes to hard 0, you can't scale that anywhere, right? Anything times 0 is 0. So you've essentially lost whatever signal this guy was carrying. As you put bigger and bigger numbers in, your maximal, he used the ABS operator, but maximum number on the left-hand side, it gets worse and worse. Over here, now we've lost, let's see, third number, 0.2 on this one here with the 7.5, and also the 0.1. So now I've lost two signals, if you will, that we're sending along down in through the network. Gets worse when we double again. Now we've lost four signals, and we really only have these four values left. So that's not going to be good, right, for us to be propagating our signal down through the network, propagating all these values and everything, adjusting weights and doing all of our other stuff. Any question on that? Okay, it's bad. Okay, so in fact, you can see here what happens. If you look at the very bottom, I'm sorry, there's a red line through it, but as these models grow to a certain size, let's say from 1.25 megabits up here to 2.7 megabits in his experiment, the accuracy just dropped off like a rock, just dropped like a stone. You get to 6.7, you're, pretty much where you started with an untrained model. You get below that and you're worse, probably than you when you started. Things have just gone to hell in a handbasket real quick. So this isn't going to work. That's not good. So any questions on that, or even understanding, it's kind of obvious why it's occurring, right? We lost the bits on the previous slide, so we're not going to be good here.
Yeah,
okay.
and Jerry, if I could just add real brief color. So we're using regular old rounding here where we just round it to the nearest things. So if you divide it into equal sized buckets, then a lot of things are going to just round to zero like you were showing.
Yeah. So this is problematic.
Hey,
okay,
Jerry,
so
any intuition why it works for smaller models but fails for bigger models?
I do not. I would be open
to. So that
Ted?
was the research that Tim Detmers did, where he showed that you get activations that are unusually large and they scale exponentially with the size of an LLM.
Okay, gotcha.
So,
Paying a model like, let's say a model is trained on a specific data set. If it introduce another data set, like for example, a model trained on medical data set, a small model that trained on medical data set, and another model that trained on, like, I don't know, people data set, then will it cause a lower accuracy?
This, if I remember the video, they were trying it, his team and him were trying it on, quite a wide range of data, sets and problems. And they saw this phenomena, if you will, occur consistently. So I don't think it's a function of the data you're training it on. The signal, it's a propagation of signal, and the signal propagation just drops off.
And this was in the basic pre-training, I think, of that OPT. So this is the generic language pre-training for that LLM. We can have whole side conversations about how you would do like fine-tuning. So if you're using things like LoRa and QLoRa, then these have basically been solved. But this is what they saw for building your general, GPT-4 or DeepSeek 3 or Claude, your base pre-trained LLM. The bigger it got,
because I heard that DeepSeek operate on like university base. Like ChatGPT is like an Einstein, and GPT-4 is like, I don't know, DeepSeek is like a university where each department handle a specific query.
Yes, it's a mixture of experts model. So that's each department having its having its own query, or many departments, because there are so I don't remember exactly how many there are experts within DeepSeek, but it's fairly extensive. So its knowledge range, its ability to learn a lot of separate, what would you call that, majors in college, is quite extensive. So, okay, I'm going to move on here. One of the things they notice is that they could, however, predict these bizarre outliers and when they were going to essentially when they were going to have problems. So they could predict it, and so they could program kind of around it. And this is a emergent of features and things like that. It'll make more sense, I think, on the next slide. But you see here, it's like you hit this wall right there. It's, I don't know, 6.5 billion parameters or something like that. And this was very, very repeatable, they said. They did it over and over with different models, and the same problem, this same graph kind of appeared. So that was kind of interesting. Okay. And so this is what they found when they went and analyzed these, that in general, the vast majority of the ones that were problematic were pretty darn few, but it was enough to just drive that. You guys saw the performance of the model way down. In fact, it was like, 0.1% of them. So what they did is, what else would you do? Give it more precision. So they just put those in 16-bit and left the ones that worked in 8-bit. And they come in, somewhere around 1% or 2% that they have to do it. They have a little mathematical equation to put these two together. All right. Go ahead.
I still don't understand the difference between 16-bit and 8-bit.
It's a question of, you remember where we started? Let's go back here. This problem here. You see, a 16-bit we would have resolved, we would not have had this 0. We would have had a value here, and we would have had a value for 7.5 and 15. But because we had this, this big value would not have caused this third value, this 0.1, to go to 0, or this 0.1 and this 0.2, if it was 7.5, to go to 0, and this, 1, 0, 3, and whatever, if you read across here, 0, 1, 0, 5 to go to 0. Just wouldn't have had that problem. You would have been able to still have these, whatever sort of signal here, because the maximal number would have been higher. Does that make sense? So
if the number is like bigger, then the math will not apply different number to you. Like
it would produce a different number, but it wouldn't produce a hard 0. The problem is the hard 0, because once you have a 0, no matter what you multiply it with, you're never coming back from 0, right? That's just mathematically. Anything times 0 is 0. So that's just what they're trying to avoid by doing all this. Does that make sense, hopefully?
Yeah. Also, I know we're talking about FP8, that specific examples that we have from Tim Detmer's slides, those are around int 8 mapping.
Yes.
So you have your numbers, but you're mapping to int 8. I'm sure there are, complications around FP8 as well, but even int 8 is difficult, and then taking it to FP8 can be another set of issues.
I'm curious to get, Dev, when we get there, when we talk about 4-bit, going to FP4, I'm curious to get your take on that. That sounds.
Do you know the specific name of the mathematical equation here?
The one right here?
Yeah.
I think it's just scaling and what is it called? Scaling and translating the zeros.
Yeah, so this is when the value went to 0. They use this guy over here. You see they're using floating point 16 throughout for the weights and everything, weight and bias and the whole 9 yards. And over here in the 8-bit, they just use the weight term over here. So yeah, that's just whatever that is, 0 point whatever, if we were to put in decimal. Okay, I'm going to move on. So what did they see? This, if you remember, this yellow one was kind of the crash thing where it just kind of all just went downhill. But when they switched to this LLM in 8 method, the blue one, you can see it tracked with their 16-bit baseline. So there was no performance degradation, which is pretty cool. Okay. Okay, but as everything, there's no free lunch here. Scaling with 8-bit resulted in loss of precision. Make quantization sensitive to outliers. In other words, the quantization can just go to a hard zero. Once again, once we go to a hard zero in multiplication, we're done. It just is not gonna, there is no recovery from that. And so we're just done. And the way they did it was to handle these with outliers with 16-bit math. But we really want FP8 because it decreases the training time. And if we do it right, we can do it with minimal loss of accuracy. So let's talk a little bit about that. So there are multiple ways of doing it. There is a library in NVIDIA that NVIDIA gives you that will do this work for you. But DeepSeek chose to write their own custom one, a rescaling kernel. And you can read through how the procedure is. And essentially, it breaks up things into little blocks and tiles. And I think that's what you were talking about, right? The block-wise versus tile-wise?
Yep, that's right.
Yep. Okay, just want to make sure, we're talking about the same thing. Tiles are two-dimensional, blocks are just like one dimension in height, and if you into height and width, and whatever n is in width. So, okay, just think of that in your mind. Yes, sir.
I'm just a little bit confused here. So tiles, I get where they're breaking it into separate tiles, each scaled differently. So if you have an outlier, it doesn't destroy everything, it just destroys that one tile, right? That other one where you did separation of outliers from the regular ones, is that something DeepSeek's using, or was that just an experiment?
No, that was Tim Detmer's experiment.
Okay.
Yeah. Everything up until here has been those slides were the slides from Tim Detmer's YouTube video.
Okay. Thank you.
Yeah. Let's see here, and you can, so we'll go into the pictures. Actually, do a better job of this than I can read in Word. They move the accumulations outside of the tensor core to CUDA cores. Tensor cores are the ones that are in the 8-bit whatever we're doing type thing. The CUDA cores are the outside, and they're 32-bit cores. Okay, as it says here, they're for parallel, generic parallel processing versus a tensor core, which is kind of dedicated. You could, if you were a graphics guy, you'd be using CUDA cores. You might use these tensor cores, but the tensor cores are really for, ML multiplications in a neural network type situation. Okay. So, and this, if you do this correctly, you can greatly reduce the training time and also minimize the loss accuracy. And we'll see that in just a minute. This is kind of what it looks like. On the left, let's see, I just want to make sure here. Yeah, we have like a scaling factor. And Ted, I think this is where I'm going to need you to help me out here. I'm not fully sure how all these work here, but there's a scaling factor where it applies it to the value and then scales it up and down so that you can cover the range that you want. Okay. And over here in the weights, we have these 128 by 128 block groups. So think of a rectangle. And, I'm sorry, the one on the left, the scaling is a tile. And it's per token of the 128 channels. So you can see this thing here where it says 1. Think of that going just down, 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 like that. Actually, no, that one's just one wide. Think of this one over here on the other side going 128 by 128 type thing. It probably, let's see here. And these are tensor core doing their operations. I don't exactly know what all this is on the slide. Apologize for that.
Yeah, I don't know that this slide doesn't, this diagram doesn't necessarily really do it for me, okay? But I mean, here's the concept, basically. I forget exactly what the smallest number is. You said the biggest number is like 447, okay?
Mm-hmm.
So the smallest number is going to be somewhere around the reciprocal of that. Let's just call it 0.002, okay? Maybe it's slightly different from that, but just, for simplicity, okay? So with an FP8, you can represent a number between 0.002 and 440 something. What happens if you have a number that's 1,000? Well, you're basically up the creek. Okay. So basically what they do is they do the same thing that we do in quantization at inference time. They're doing it at runtime. So if you have a bunch of numbers and they're all between 1,000 and say 440,000, no problem. Basically, you just divide everything by 1,000. And then we can represent them easily with FP8. So the only time you run into a problem with FP8 is if you have a range of numbers where there's really big ones, like over 1,000, and there's also really small ones, say numbers that are like 0.0001. That's basically impossible to represent accurately with FP8. You're going to get, as you pointed out, Jerry, the small ones are going to round to 0. And that's going to be problematic. But
that's loss of signal right there.
So what we do is we just choose a chunk size. In this case, they chose 128, where the odds of getting really big and really small ones at the same time become very, very low. It's probably not never, but the odds of it become really low. And obviously there's some cleverness in terms of how they pick the arrangement of these and whatnot. That's why you see sometimes they just do a row of 128, sometimes they do a square, 128 by 128, okay? But the general gist is just that you want to divide it up into small enough chunks so that, okay, fine, you've got some big numbers, great, we can handle big numbers. Oh, you've got some really small numbers that are like, 0.0001, no problem, we can handle that. As long as you don't have both, we're good. We're just going to basically have a scaling factor that says, are these numbers all really big or are these numbers all really small? And that scaling factor, I don't know what it's stored in, but it's going to be stored in something like 16 or 32-bit so that it has a very wide range it can support.
Basically what I understand from your presentation, like for the tensor core, instead of like you have a whole range of numbers from 1 to I/2 to 437, and if you multiply it by that, it will have an increased chance of a 0 occurring. And for the CUDA core, you just split the amount of calculation, like for a block, you just cut the block into separate pieces and you calculate one in each of those pieces to avoid a 0 number situation. Is that correct?
Yeah, and it's really not 0. It's just you don't want anything to be too big, you get an overflow. And you don't want anything to be less than 0.02 because then you get an underflow and it rounds to 0. So both of those are bad, both the overflow and the underflow.
Just out of bounds type condition. Or phrase it.
Yeah.
Okay.
So that's the thing is in vanilla mixed precision, when we use 16-bit, we don't do any scaling. We don't do any normalization. We just literally say, rewrite this number as a 16-bit number instead of a 32-bit number. Okay. Right. What here they're doing is they take these 128 numbers, find out what's the biggest number, what's the smallest number, whatever, rescale them, and then write the rescaled numbers that fall nicely in the range between 0.02 and 447. Write those as 8-bit numbers. Do all your math, and then when you're done doing the math, we have to scale it back to whatever its original values were. So if we divided by 1,000, we have to sort of multiply by 1,000 once we get the result in order to get back the raw numbers. And that's where the storing it as a 32-bit number, we're storing the raw numbers that are scaled back to their original size.
Hey, Jerry, did they talk about how they handle outliers?
Well, this whole thing is about outliers. I guess I'm not handling outliers, Dave. What specific issue? And maybe I'm not understanding what you mean by an outlier in your context.
Yeah, so they have these groups of 128 for the activations, and then tiles of 128 by 128. Sorry, the other way around, the tiles for activations and the blocks for weights. With the assumption and hope that, these are able to accommodate the quantization without any outlier issues, like not too large and too small in the same tile or same block. But it may not always be guaranteed. Do they do some? Oh, they say that this better accommodates outliers by adapting the scale. I mean, that's the hope, but you still could have outlier blocks or tiles.
I don't think there was anything in the paper. I think, like I said, they chose 128 to be small enough that the odds of an overflow or underflow are really small. And if you think about underflow, if you're doing a batch, right, you're averaging the gradients across multiple items. So if one of them zeroes out, that's not like the worst thing in the world. You're not, you don't necessarily have a super hard zero, but you don't want, like Jerry was saying, to get a zero early on in your forward pass and then just somehow
you lost the signal forever.
And then you're just doing zeros, forever and ever and ever down the road, right? So I would imagine that you can tolerate a certain very small percentage, 1 out of every, million. If it has an overflow, underflow, you just ignore it, and it probably works out okay.
Yeah, and I think Go ahead.
The reason I mentioned that is because sometimes, since those are very rare occasions when you may still have outliers, because it all depends on the size of your quantum here. In this case, let's say 128, right? If you make it smaller, 64, the chances may be even lower that, if you have bigger blocks and tiles, bigger quantum, then the chances of having outliers is higher and more degradation of performance. But then if you go lower, then you may have more tiles of blocks that may have potentially outlier. And I know that sometimes they say, okay, let's say 0.1 tile, a percent of your tiles and blocks have outliers, and we'll just handle those separately. But that's okay. I was just wondering if they had anything like that. But thank you.
Okay.
Yeah, I don't think they had anything that says if something happens, do this other thing. It's just no. We hope that it's rare or never.
Yeah. Thanks.
Yep. Well, you said, as Tim Detmer's thing said, you're talking he saw 1%, right? Isn't that what he said on his thing? So it does happen, but it's pretty low probability. Okay.
Yeah, and for that small probability, I'm okay to pay that extra compute.
Yeah. So what would the mediation be, right? It would be,
that's what I was asking.
Yeah. Just let's do it again in 16 or something like that. I mean, that could be a mediation, right? So let me back up. That could be a mediation or something like that. We just kind of shuffle it off, upscale it, and shove it through, and Bob's your uncle kind of thing, right? As long as you're not doing that too often, I suppose.
Yeah.
Yeah.
Thank you, Jerry.
Yeah. Moving on. So on DeepSeek, so they did this custom quantization, and I think there are several things going on here because there actually is an NVIDIA library to deal with this, but they chose not to use it. NVIDIA, it's very much a black box. I don't know if NVIDIA provides the source code for the libraries, but everything I saw documented, it just said, call these like 5 functions or something like that, and they do this for you. But DeepSeek actually chose to do their own kind of sort of thing. Do I need to go back? Let me see here. Nope. Oh, no, we're good. And I think they did it because a couple of things. First, if you remember, they were kind of late GPU, high performance GPU constrained. And this lets them, because they are writing the code at a low enough level, like, assembler level on top of these boards and things like that, they could probably move them, put these routines where they wanted on what preceded, I forget what preceded the Hopper family, but whatever the 3090 level GPUs were and things like that. And that they also that let them use non-export restricted GPUs, because you remember the whole China export ban type thing does block some variants of the Hopper family. And they could optimize their code to work best on the available hardware. Now, this is me speculating. I've seen nothing that says that this does, but they went through all the trouble rather than calling an existing library that NVIDIA had, invested money in. But hey, by the way, FP8 only works on Hopper. So if you don't have an Hopper, you're SOL, right? So you've got to do something. So my guess is they, because of the restrictions and things, that they had to go through some of these gyrations. And then by having the code themselves, they don't have to worry about, if there's a bug, we got to call NVIDIA, and NVIDIA's, file a bug thing with NVIDIA and they'll fix it or something like that. No. We're gonna write to the metal ourselves, and we're gonna do it. And that's not a bad, if this is a correct conjecture, that's not a bad way to go to be able to control your destiny, if you will, or prevent somebody else from tripping you up because, NVIDIA won't sell you the damn board or whatever. So that's just my 2 cents on it, but I think it's...
I'm just reading through on the infrastructure. They talk about using 2048 NVIDIA H800 GPUs. Is that a Hopper family?
I don't know I'm sure if you look up the H800, you could find out. It may be, I'm trying to remember who was before Hopper. Shoot. Anyway.
Wasn't there like Turing and Ampere before that?
Ampere and then Turing, I think it was, Ted, if I'm not mistaken. But it doesn't really matter, right? It was one of those two. So, and those, were freely exportable. So they could get those. Because they went through a lot. This is a non-trivial, you got to imagine, this is a non-trivial bit of work, and it also, so they went through a lot of effort to do this. The other thing it brings up, though, is what if you don't want to use NVIDIA anymore? Well, you got the code, right? Or at least you have the understanding of what you did with the code. So if, somebody else comes out with the latest and greatest GPU, Tencent, is that the company in China that's coming out now and wants to go head to head with NVIDIA on GPUs? I believe it's Tencent.
It is Huawei, and
Huawei?
the name of the product, Huawei, and the chip is Ascent 910 and 915C or whatever.
Yeah. So there are competitors, to knock off NVIDIA, right? So if these guys have their code and they can port that code to that new thing that maybe and even optimize it to run better, they can cut the NVIDIA moat. And there's in prepping for this, I was surprised how many people had said that, NVIDIA's moat's going away. So maybe this is one of the ways that, people are looking at doing that. So anyway. All right. For them, though, they could, use optimizer code as required to work with available hardware, be that NVIDIA or somebody else. And obviously, they could use the older versions of NVIDIA hardware because the older versions did not support this quantization, so the FP8. So
regarding the third bullet, they did mention in the paper, if you go back to the previous slide,
there we go.
So so I just pasted in the chat channel a clip from their paper where they found an issue with the precision management with the gem library of FP8 gem library that NVIDIA had, and they were truncating the precision to 14 bits. So they have a suggestion for NVIDIA to do it better in the future versions. So now with their own implementations, they can decide to do whichever way they want to do possibly. But go ahead.
Yeah, so there was talk, I must have looked at 40 videos, on all this, and a number of them talked about, this, wanting to be master of your own destiny type thing. And, that these guys had sent a laundry list of things to NVIDIA saying, you know, you guys should do this and you guys should do this. And it pretty much tracks with what they did. So it's kind of interesting. Anyway, one of the things that they did also was, you know, when they move, if they can't do the operation in the tensor cores, they move it out to a CUDA core, which is the older style one, and it is a 32-bit register. So they just move it off this one into a CUDA type core to produce a 32-bit output. Let's see here.
This is the one where the accumulator wasn't sufficient precision.
Yes, yes.
Yeah.
Low precision accumulator, and they don't call it a high precision accumulator, but it's the lack of a low precision. Yeah. Okay, we're just about finished here, so finish this. So in summary, when I looked at this, I thought that they did a good advantage, taking advantage of the features that NVIDIA offered to speed the training. They obviously substantially reduced their training time and costs, giving them what do we come out with, 1.5 or something like that times improvement. That's nothing to sneeze about. And they took advantage of the Hopper features when they could, because those what do you call when you embargoes on some of those ones? Some of the Hopper ones were early Hopper models were not. Later Hopper models were. So they could use those and things like that. But, they're going to have to worry about that with Blackwell coming out too. Are they going to be embargoed against that? They did not use the NVIDIA libraries and wrote their own. And this, gave them a method that worked on multiple accelerator generations. So that, in my opinion, is a smart business decision if you have the wherewithal to do that. Because NVIDIA is going to get knocked off the top of the heap one day, right? We know that's coming. We don't know when that's going to come, but at some point they're going to get knocked off the top of the heap. And then everybody that's so hooked into the NVIDIA libraries is going to have to rewrite a whole bunch of stuff. And that's going to be a fairly, and retest, right, all their models and things like that. That's going to be a very expensive process. These guys, maybe not so much. Anyway, last line then, can't wait to see what they're going to take advantage of, if they will and can take advantage of floating point 6 and floating point 4 in the new Blackwell chip that is shipping, I believe this month, or shipped last month out to early preview type people. So that's coming out. That's the new NVIDIA that replaces the Hopper. Okay, questions? Because that's my presentation. Discussion.
So the overall performance gain was somewhere around 0.48 or something like that, then, is what we get out.
Let's see. That was...
Although we get a smaller memory footprint, I assume, right?
Yeah. Yeah, so it's a win-win on both, both things. Yeah, here it is, a 1.4 at 1.5. And I don't know that that's an optimized number, Roger. They may actually be able to do a little bit better, but this is the number I saw bandied about.
Okay.
So, but still, that's nothing to sneeze at, right? When you're talking,
and if the model is close to a factor of 2 smaller, then that's a big win too.
Yeah. You're lighter, faster, and it takes you less time to produce another version of it. An new and improved version of it. I mean, there's no negatives in all of that,
Yeah. And is it, Ted, you said something about being able to just kind of switch to this mixed precision. So if I have a little model I want to train and I want to try using 8-bit weights, is there a standard way to do that, like in the Transformers library?
Today, I don't believe so. So we started out training everything in FP32, and then it became so popular to do 16-bit that instead of you having to do it manually, eventually there became library support for it. So now there's just what's called automatic mixed precision, And I believe basically all of your weights are 16-bit and all the gradients are 32-bit is the general gist of it. But basically when you import something, it has internal tags that say whether this thing should be small or big. Right. So like for example, I don't know the parameters for Atom, like whether the momentum is 16 or 32, but I'm pretty sure basically the Atom object basically just tells PyTorch, hey, I want this one to be full 32. And somebody else figured that out, so you don't have to. You just can basically write approximately 2 lines of code to say you want automatic mix precision. So at some point, if this becomes validated and popular, there may be a new automatic variant that uses not just 8-bit, but quantized 8-bit. So there's that extra overhead where you have to scale it before you do the 8-bit multiplies, and then you have to, I don't know what the word is, unscale it, restore it when you're done. So there's that extra work. So you wouldn't really benefit from this for a smaller model. You would really want a really ginormous model so that the amount of matrix multiplies you're doing justifies that extra bit you need to do on the ends.
Right. Okay.
Yeah.
And you say the way it works now is like you kind of define your model independently, and then you say, okay, here's my model and expressions 32-bit. You go and insert the right data types.
Yeah. So what I'm saying is you can manually say what precision you want, but if you use automatic precision, then basically when you say, I would like a fully connected layer, I would like a transformer encoder layer, the people who built those layers have already tagged them as what the default precision is for automatic mix precision. So basically, as long as you believe that they did it right, you don't even have to say, store this one big or small. Somebody has set the defaults for every object that you're just including in your model anyway.
Cool.
So you're talking, though, Ted, at the language level object, right? Or a library, maybe referring to a library, or?
I'm just saying, if you say, I want an LSTM, I want a transformer decoder, I want a whatever, then they have parameters, right? And so somebody has defined, is it okay for that parameter to be 16-bit instead of 32?
Right. Yeah, because, when I showed this stuff here, where I said they wrote their own custom type thing, there actually is, NVIDIA does provide a library, obviously a much lower level library that sits pretty close to the hardware on that. And they chose explicitly not to use it because...
Yeah, I don't know if NVIDIA does do the block-wise rescaling whole business, but if not, it's probably just because they have older GPUs and they needed to write it anyway. But what I'm saying is that the current support in PyTorch that I'm familiar with has no rescaling. It's just use a smaller container for this number, and then the number, cannot be bigger or smaller than what it supports.
I see. Okay. Yeah. I think this sort of level of programming is something that whoever wrote PyTorch, that PyTorch function, they'd be the one calling that, I think, if I understand this level correctly.
Right. Yep. Yeah.
And then you'd call the PyTorch function.
Yep.
Yeah.
You'd have to do it manually.
And you'd have...
If I remember right, QLoRa, I think, does do block quantization. So it will not just quantize all of your weights. It'll do it in smaller chunks. And so this is not like a brand new concept.
Yeah. Because, when I was first starting this, I read through this, I said, so I actually had my Hopper, API type thing. I was looking at Hopper API pages. And then I started realizing that, hey, these guys didn't use this stuff, They did something else. And that was really kind of eye-opening to me that they, A, had the skills to do it, B, had the resources to do it, and C got better results because they did it, you know? So that was really sort of an interesting, eye-opening moment. And I guess it just shows you if you've got the resources and things like that, because there's no way, you know, some startup in the Valley is going to have probably the resources to do that, right? Unless they're, well, I guess they could be that well funded, but let's say small startup probably wouldn't have the resources to do that. It takes somebody with some pretty deep technical bench to do that, I think.
Yeah, I'd characterize it more as the skill set rather than the resources, because it seems like that's one of the patterns we've seen with DeepSeek is that they've gone in and done optimization. It's just engineering. It requires a specific skill set, but it's not necessarily much more expensive than not. But they've spent the time to do that optimization at the very low levels.
Yeah.
For whatever reason, whereas other companies have just bought more GPUs.
Yeah, well, you know, but I guess my point is, if you look at the funnel of developers, right? There's a lot of, you know, if you look at the number of people that have the skill to work at that level, that's getting to a little bit more rarefied air, if you will. You know what I mean?
Yeah.
It's not your average guy that went to, you know, some local college and got a degree, type thing. You know, it is somebody that really lives with a foot in the hardware world and in the software world and understands them both, I think, fairly well. So yeah. And those people are not just, you know, your average person you find. So anyway. Okay. Anything else?